Thanks very much, everybody. So, first of all, I think you know you're in the case studies track when you have a title which spans across 4 lines of the title page. So, apologies, there's a little bit to unpack here in terms of what I'm going to be talking about today. But I wanted to share with you something that we have been doing as a collaboration with GSK, one of the pharmaceutical companies in the UK. And our goal has really been to explore how an end-to-end pipeline, which is data-driven in nature, could benefit from quantum computational calculations which naturally will lend themselves to being scalable on quantum hardware, with the view that we may be able to improve some of the data-driven models and also bring some of the value from quantum computing a little bit closer. So I hope to unpack this and share with you what we've been doing, and also share some of the unanswered questions in this space. So, those of you who attended Julian Van Velsen's talk yesterday may have seen this slide already. This is kind of a view of how we see a pipeline like this potentially working. So you see the first part of it is focused on embedding, and this is how we are exploring relevant parts of chemistry, of molecules, that we will be able to put on quantum hardware. So part of our goal is to be able to make contact with what we can do on quantum computers as soon as possible. Typically, drug molecules are rather, even small molecule drugs are rather large, and so we need to focus on active spaces which are somewhat smaller. I'll say a little bit about that. The next phase is how do we extract some features from those molecules which are going to be useful in terms of predictive modeling, and how can we do it in such a way which naturally lends itself to the sorts of things which quantum computers can do. And then the final part is on exactly how we can use some of that data. And what I'll do is hopefully show, for a particular task that we've been looking at, some of the results at small scales today, which we're quite excited about and think are promising. So if you attended Julian's talk yesterday, you'll see that he mentioned a range of different areas, kind of building blocks that could fit into all of these pieces, and the aim of this talk is to be concrete about some of them and give an end-to-end example. So let's talk about the particular problem at hand. So we had some great conversations with GSK, and we were kind of exploring some of the challenges which are tough today to apply data-driven techniques to. And one of the areas that we settled on were covalent drugs. Now, covalent drugs are quite interesting. These are molecules which form covalent bonds with reactive groups on particular amino acids, on target proteins. And one of the great advantages is that, therefore, you can have drugs which have really rather high potency. And, of course, this means smaller doses. So exactly what Clemens was talking about in the first session this morning. Now, there are a number of different kinds of covalent drugs, a range of different chemistry, but what they have in common is that they have a reactive group, which is usually called a warhead. And actually, I've in the past tried to put that in the title of a talk, and people have pushed back on me and said, please don't put warhead in the title of a talk in this space. So when I refer to warhead, I'm talking about a reactive group on a molecule. I'm not talking about something from a completely different topic altogether. But anyway, there are multiple different kinds of warheads, and working with GSK, we identified that sulfonyl fluoride chemistry might be an interesting problem to tackle. And these are some of the molecules from a chemical series. You may be able to see they all have this sort of this yellow, blue, and red group. This is the sulfonyl fluoride warhead. And this is the bit that binds strongly. So we chose this because it's quite well understood by them. It's one of the simpler examples of a class of covalent drug within this category. Okay, so let's turn to the end-to-end pipeline. And I want to talk through the different stages, the different things that we did with a view to tackling this kind of challenge and actually trying to predict the reactivity of that series of drug-like molecules. So the first phase is embedding. Well, there are multiple ways that we can find effective models for chemistry which allow us to focus in on a key region of interest. We applied a technique called density matrix embedding theory, and what this does is enables us to separate our entire system, our entire molecule, into a cluster of interest and a wider environment. So this is a part of the molecule that we're interested in, and the rest of the molecule, which we'll capture to an approximate level of detail. And specifically, that cluster in the middle can actually be separated into a fragment and a bar. So the fragment is the bit that we care about, where the chemistry is really interesting. And if you like, the interactions with the surrounding regions, so exchange of energy, potential exchange of particles, can be captured by a bath, and we have full quantum coherence between the fragment and the bath. We capture all of the many-body correlations. And I was told not to put a Hamiltonian in, so I'm not going to talk about the Hamiltonian, but the only thing I'm going to say is that basically we have an effective model which looks like a normal electronic Hamiltonian, so we know how to deal with that in this kind of context. I'll just show what that looks like for one of these molecules. This is a molecule you can see on the left-hand side. This is the fragment. This is the reactive group. This is the warhead, the sulfonyl fluoride warhead. And actually, this is common to all of the molecules in the data sets, because we're looking to predict the reactivity of this particular kind of covalent drug molecule. So this is easy enough. The bath then is actually formed through the density matrix embedding theory from the rest of the molecule, and it's chosen to capture those interactions. And then everything else is described by an environment, which in our work we treat at a mean field level. So the idea is that there's a part that we can simulate exactly, at least at the level of the basis set that we're capturing. So for that active space, we can treat it exactly, and then everything else we can treat approximately, and this may be done on a classical computer. So that's kind of the embedding approach at a high level. Let's talk a little bit about how we extract some features. And this is such a broad topic that there are many things we could do. But what we tried to focus on was some of the things which quantum computers are naturally going to be good at. And you'll see, well, let me talk you through this slide. So what we do is we prepare the warhead in a particular reference state. We apply some kind of state transformation to it, and then we measure some observables. And that kind of top line could really describe any quantum circuit at that level. So let's dig into a bit more detail. What we actually do is we use the unitary which describes the evolution of the warhead under the density matrix embedding theory Hamiltonian. And what we do is we evolve it, we take measurements, and we capture these for all of the different molecules, and this allows us to compare the different molecules. So the particular feature that we're looking at here is essentially the fluctuations in energy of single particles on the warhead. This is what this feature really means here, and you can see we get a load of wonderful temporal trajectories from each of those molecules. So this is the more mathematical view. Let me again switch to the pictorial view. This is just showing two molecules where they have the same reactive group, but the rest of the molecule is different. From the same reference state, we can see changes in the electronic density over time. These are hugely exaggerated. This is why these animations look a little bit odd. But the crucial thing is you can see that the left-hand side and the right-hand side are different. And their Fourier spectra are on the bottom. So the idea is these behave like fingerprints for the molecules, quantum fingerprints. And if we have two quantum fingerprints from warheads which are very similar, then we expect that the chemistry should be similar. They'll behave similarly with regard to how they react. And of course, if they're different, then we'll see different fingerprints. And of course, this is where machine learning comes in. It's very good at mapping the space of differences and making useful predictions based on it. So that's kind of the goal here. And if we put all of this together, this is kind of what we have. First of all, the ability to take a molecule, identify this fragment of interest, which is in this case the warhead group, which is on the left-hand side here. We're selecting those atoms. We can then apply the density matrix embedding theory approach. This generates us some bath orbitals. In a second, you'll see we can look at those, we can explore them, but crucially, we can then generate a quantum fingerprint that we can use in downstream data-driven modeling. So that's kind of the aim here. These are results from a quantum simulator, and everything I'm going to show first of all are purely from Hamiltonian simulation on quantum simulators. So this feature will pop up, which in this case is the Fourier space version of this fingerprint for this particular molecule. Okay, so that's what we're doing to generate these features. The next question is, are they useful? Can we do anything useful with them? Are they predictive? Well, maybe I can show you some of our very first results. So in this data set, there were 8 molecules which had experimental data for reactivity, and we just looked at, this is just kind of half of that Fourier space plot, and we noticed that 7 of them had a dominant peak at a particular position, and 1 of them had that peak quite shifted from the rest of them, and a natural question was, is there any significance to this? Did we do something wrong? Because all of the molecules look somewhat similar. You can see all of these molecules have this, this reactive warhead group. They've all got this kind of red, yellow, and cyan-colored group there. This is the SO2F group. And each of these is connected to some kind of aromatic ring, so they all look somewhat similar. And if we look at the other one, which is kind of the odd one out from the quantum features, it also looks kind of the same. We can see that it's got a warhead group, it's got an aromatic ring, and it's not completely obvious what's going wrong there. But then we looked a little bit harder, and actually we spotted that actually this has an additional oxygen. So this is actually a fluorosulfate, not a sulfonyl fluoride. And really, this is actually a different class of warhead. So this was somewhat of a mistake. This really shouldn't have been in the data set to begin with because it's part of a different chemical series. So we were quite reassured that we could spot this without even realizing it and identify that these quantum fingerprints actually capture something that's relevant. Okay, let's dig into some predictive modeling in a little bit more detail. We wanted to try and see if we could predict reactivity from this description of the fragment and from these dynamical features. And essentially, we got some nice results. So this is what this is showing you here. This is showing sort of predicted versus actual. And we have an explained variance, which is really high. Now, there is a little bit of a caveat to this, which is that not all of the molecules in this data set have experimental reactivity. So actually, what we had to do was use classical simulations for the entire molecule as a kind of a reference point for some of the data in place of experimental data. However, what's nice is that these are simulations of the entire molecule, and we are capturing features on really relatively small active spaces involving just the dynamics of the warhead, the part that we would like to put on a quantum computer. So we were really pleased to see that actually these are predictive. And we did a range of different studies around this. So one of the things that we were interested to do is sort of explore how this approach scales in different ways. So one of the things that we naturally thought was that if we get richer feature vectors, so richer quantum fingerprints, we will get better predictive models. And one of the ways to do that is to evolve the system for longer and sort of repeat with different time points for these measurements. And what you're looking at here on the top is the explained variance, and the bottom is mean squared error. And you see that actually, yes, the models improve as we evolve along the x-axis for different times. And there's actually an interesting step here, which seems to correspond to a time scale which is associated with the typical bond energies in the sulfonyl fluoride warhead. So that's quite pleasing to see that there's a sort of time scale beyond which we can capture energy scales relevant to the problem in this way. We also looked at the different active space sizes. So one of the things that we can explore is how many orbitals we keep, how many electrons we keep in our description for the fragment when we evolve it. And what you're looking at here is a size of 4, a size of 8, and a size of 12. So kind of the 12 being 6 electrons, 6 orbitals, so 12 spin orbitals. And you can see that on the left-hand side, the explained variance increases, which is great to see. And on the right-hand side, the error of prediction falls. So we are seeing a progression as we go to bigger active spaces, which is what we'd want to see. So I'm well aware that obviously we're kind of predicting a proxy in this, and one of the things that we're keen to do is validate this on more experimental data, and in particular look at the situations where our model predicts something different from the classical calculations. These are good data points to go and actually measure to see where they differ. But I wanted to share something else with you, which is how we can use these fingerprints. If they're really meaningful fingerprints, then they should allow us to explore the chemical space in a meaningful way. So one of the other things that we looked at was clustering. Apologies, I'll come on to that in a sec. But before I do, I just want to mention, we have, of course, tried this on quantum hardware. We have been looking at IBM hardware to explore how we can do this temporal evolution at small scales today. To do that, you divide up, one of the ways to do that is to divide up the time evolution into small slices and basically evolve the system as a series of steps. This is a so-called Trotter-Suzuki approach. And we have a trade-off here, because if we have a large number of steps, then we have very good accuracy in the sense that we are closer to the true quantum evolution. But this gives us a longer circuit depth. And you can kind of see here on a simulator, this is for two molecules which are really chosen to be really rather different, even with a small active space dimension. The features look better the greater the number of steps. Molecule 1 looks more different from molecule 2, but we can still pull them apart, which is one of the things which is pleasing. And of course, we tried this on quantum devices as well. And I guess we're at the stage where, with error mitigation techniques off the shelf, we can just pick apart two molecules which are rather different. So if you look, the black curve here is the ideal result, where we see a difference in the fingerprints. The orange and the green curves are using a couple of different off-the-shelf error mitigation strategies, and by the time we reach long enough times, we can just about pick them apart. But really, there's quite a lot more to push here, and actually, in a scalable fashion, these product formulas like the Suzuki-Trotter approach are not really the right way to go. Okay, now to the clustering. So here we can see that actually, if we look at these fingerprints in the time domain, they do naturally fall into different clusters of molecules, and we can dig into those into a little bit of detail. So if we look at cluster 12 here, you can see these contain naphthalene compounds, so the two benzene rings fused together. If we look at another cluster, so let's take cluster 9, we can see that these are, for example, include some thiophenes. These are these 5-membered rings with substitutions. If we look at cluster 4, then we see a series of sulfonamides sort of substituted across from the warhead, so kind of at opposite positions on the benzene ring. So these quantum fingerprints are naturally capturing some of the differences in the chemistry that we would expect to see. So that's really nice to see. Of course, that doesn't necessarily push us beyond what we could do with classical fingerprints, so it may not be super exciting. But actually, if you look within several of these clusters, you find nice counterexamples. So if you look here, there's a molecule 161, which is right in the middle here, and this is actually an amide, not a sulfonamide. So classically, the collection of atoms are somewhat different. The classical fingerprints will look really not the same at all. But actually, the chemistry in terms of the reactivity of this reactive group is somewhat similar. And this is one of the things which excited the chemists at GSK quite a bit, because we were providing a meaningful clustering with regard to the behavior of the reactive group from an underlying quantum description, which is really exciting. OK, I'll just say a few comments in terms of next steps. So quite a few things that we're doing next. One of them is exploring a wider pool of applications, including some outside of the life sciences area. There are plenty of areas where we want to extend this approach. In particular, this is an easy example because there really is a common functional group across the entire data set. We also want to look at kind of optimizing the algorithmic approaches, and there are multiple things to do there, but I guess I hinted at one of them, which is the fact that it may be that we don't need strict unitary evolution for this. We may be able to create other unitaries which are more efficient in terms of being able to use quantum resource more effectively, but still separate the space of molecules and make meaningful predictive models. One of the things that we're looking at now already is actually selecting the measurements based on the data, so data-driven measurements at the end of the circuit, and this is kind of a step towards QML as part of the overall pipeline. We've played with this already in toy problems. We have some work looking at the robustness. We want to sort of map out quantum resource requirements in a little bit more detail. So several areas to build on the work that we've already done in this area. And I just want to finish by thanking not only the Capgemini team, but also our collaborators at GSK, who are absolutely central to making the project a success. We're also very grateful to get a little bit of support for part of this project from the STFC in the UK and the UK National Quantum Computing Centre. And I have to say, Those guys were absolutely fabulous to work with. We had some really interesting conversations about the chemistry and about the computational approaches. And I'll just leave you with this slide. If any of this is sort of interesting, any of the next steps, this whole topic of end-to-end pipelines where quantum could play a central role, we'd be really excited to collaborate with you. And I'll finish there, and thank you for your attention.
One question for Sam.
Why would you do any of this on a quantum box? This is classical TFT, void optimization.
So the feature extraction captures the full many-body correlations of the embedded model. And so therefore,
all that optimization with DFT.
but you can't capture the full many-body you can't capture the full many-body correlations of a fragment Hamiltonian with DFT. You have to make some approximation in terms of those. And so therefore, this is a method that will naturally scale to be able to capture those differences in terms of the feature set.